Okay, so some of you have already submitted the homework and they look great. So I had a question in the homeworks and I thought it was so good that we should discuss it together. So I'm going to start off by quickly going through stuff that you will have learned in your first quantum field theory course. It's if you did my YouTube quantum field theory course, then we did cover it there. So I'm just going to review this quite quickly, um, and then get to the question. So I'm going to start off by giving you a reminder on how we derive the Kalan-Samanzik equation. Then I'll discuss how we solve it. Then I'll tell you what is the puzzle, the question that I was asked in the homeworks, and then we'll talk about the resolution of it. Okay, so basically, we're thinking about quantum field theory. We're thinking about how to renormalize it. So for concreteness, let's start off by considering a theory described by the following Lagrangian density. I should stress that the discussion that we're going to make now is quite general, but I am considering this Lagrangian for definiteness. So with minus g phi to the 4, I am working in Minkowski space. And just to remind you how we talk about things, we say that the bare coupling and field appear inside this Lagrangian. So part of what renormalization is doing, it's telling us how to relate the bare coupling and the bare field to some physical field and some physical coupling. So what kinds of things do we like to calculate? Well, the basic quantity we would calculate is a Green's function, a correlation function. So it would be the time-ordered uh, product of n of these fields. So this is the basic observable that we would calculate. Now, this is of the bare field. And that's the bare field has a field strength that you would not measure. So what field strength would you measure? You would measure a field strength of the physical field. And the physical field is related by a factor that we usually call z. It's called the wave function renormalization. It's z to the minus 1/2 times by phi. And this number z lies between 0 and 1. It can be equal to 1, but if the wave function in normalization is equal to 1, you have a free theory. So I'll put a less than or equal to here, but remember, that just means that you've got a free theory if it's actually equal to 1. To renormalize, so let's just remind ourselves what we do. So to renormalize, we would choose a scale m, choose a scale m. We want to define these two objects in terms of physical couplings and fields. So we need two conditions, okay? So we would take the 2-point function in momentum space now. So imagine that I have taken a Fourier transform to momentum space, and we could set this equal to, so we would set this equal to I over p squared. Now, this can't be true at all momenta, so we would choose to do this at some specific scale. So let's say at p squared is equal to minus m squared. So this would be our first renormalization condition, and this would be the two-point function of the physical field. Okay? So this would be a two-point function of the physical field. To denote two-point functions of physical fields, let me put an R here to say it's been renormalized. Okay, so that's the first thing that we would choose. We would also then put a condition on the 4-point function. So what condition would we put on the 4-point function? Well, I'll again write it in momentum space. So we would say the 4-point function, let's again put an R here, of P1 up to P4, so it'll depend on 4 momenta. And I only want the connected piece. So that's why I put a subscript connected, and I'll put a prime here to indicate I drop the external legs. So it's amputated. And this will be equal to minus 24i. And now this is the physical coupling. This is some parameter that you managed to cleverly measure from experiment. And again, this must be done at some specific kinematical point. So we'll say at P1 plus P2 squared is equal to, this is a pretty standard choice for this kinematical point. You can look at my YouTube lectures of last year, or why don't you go to something like Peskin and Schroeder, which is a textbook that I like very much. And this is equal to minus m squared. Good. Okay, so I have just told you what it looks like. And now let's write down explicitly what this renormalized correlator is. Let's be clear on this. So I've got this correlator, Gn renormalized. This will be a function after I have completed this exercise of the physical coupling and the scale m. Those are the two things that it depends on. And what exactly is this equal to? I'll write it now in position space. You know, you guys can freely go between position and momentum space with the Fourier transform, but don't get hung up on whether I'm in position or momentum space. You know, you easily know how to go between the two. So that's the renormalized correlation function. And this, of course, is also equal to z to the minus n over 2. And now the correlation function of the Baire fields. Good. Okay, so now let's come to derive the Kalan-Samanzik equation. So what is the Kalan-Samanzik equation? If you like, one way of saying things is that the Kalan-Samanzik equation, so let's maybe just write the Kalan-Samanzik equation is a consistency condition that this above picture that I've just described to you makes sense. So how do you derive it? Well, let's think about it like this. So let's say I'm renormalizing the theory. Okay, so this is me. I will choose to do things at a scale m. Well, I will choose to do things at a scale m. I will have a wave function normalization. I'll specify it by log z. You'll see why it's more convenient to work with a log in a moment. And I will have a physical coupling. On the other hand, you also normalize the theory, but you decide to do it at a scale of m plus delta m. Your wave function in normalization is log z plus delta log z, and you choose your coupling to be g physical plus delta g physical. So you've got slightly different renormalization parameters to I do. So what is the Kalan-Samanzik equation telling us? Well, you and I are studying the same theory. So we must get the same observables, which means we must get the same renormalized correlation functions. Okay, so we want to get, so we must get the same renormalized correlators. Okay. So we must get the same renormalized correlators. And this is going to give us an equation for these changes, the delta m, the delta log z, and the delta gp, and that is the Kalan-Samanzik equation. Okay, so let's see how to do this. Well, the change in the Green's function, oh, sorry. So we can think about it in two ways. So the first way I'm going to think about it is, look at this first equality. Where was it? Okay. Look at this first expression over here. We said that this renormalized Green's function, a normalized correlation function, is a function only of GP and M. Now we've changed M and we've changed GP. So just by doing the standard kind of expansions that we would always do, this is one way to write down the change in the Green's function. Okay? So that's one way to write it down. But of course, there's a second way to write it down, because we might also look at this equation over here. And in this equation over here, that correlator of the bare fields doesn't depend on any of our renormalization conditions. The dependence on our renormalization conditions only comes in the z to the minus n over 2 factor up front. So let's think about how that z to the minus n over 2 factor changes. So we could write z to the minus n over 2. What is this equal to? This is e to the minus n over 2 log z. And how does this change? Well, this goes into e to the minus n over 2. And now we will get log z minus n over 2 delta log z. And then this is equal to, so that e to the minus n over 2 log z is just z to the minus n over 2. And then I'll expand e to the minus n over 2 log z. So I'll get 1 minus n over 2 log z. And we'll forget about log z squared, as we did for the blue equation above. Now, so first of all, it's this equation in red. This is the reason why I changed from z to log z. And then second, we usually introduce a little bit of notation to simplify things. We say that log z is equal to, delta log z is equal to minus 2 delta eta. So that this equation in red becomes z to the minus n over 2. This will go 1 plus n delta eta. Okay? So this is how z to the minus n over 2 changes. So there's an alternative expression that we can write down for the change in GR, and it is n delta eta g n of r. And the equality between the blue and red expressions on this slide is the Cullen-Szymanczyk equation. Okay, so that's the idea. Okay, we will continue in a moment.